So far, we have been discussing vectors in Rn, which is the set of ordered pairs x1, x2 up to xn, where each xi is a real number. The set of scalars is the real numbers. More generally, we can work in Cn, which is the set of ordered pairs x1, x2 up to xn, where each xi is a complex number. The set of scalars is the complex numbers. We introduce another set of scalars, called f2, which equals the set 0 and 1. Addition and multiplication are defined as expected. That is, 0 plus 0 equals 1 plus 1 equals 0, 1 plus 0 equals 0 plus 1 equals 1, 0 times 0 equals 1 times 0 equals 0 times 1 equals 0, and 1 times 1 equals 1. We can use this set of scalars on the set of vectors f2 to the n, which is the set of ordered pairs x1, x2 up to xn, where each xi is in f2. Addition and scalar multiplication are defined component-wise, like in Rn and Cn. Now, we formally define a vector space. A vector space V over F is a set V of objects, called vectors, and a field F, where F equals the real numbers, complex numbers, or F2, such that addition and scalar multiplication are defined on V. In other words, there exist functions v cross v to v for addition and f cross v to v for scalar multiplication, and they satisfy the following axioms. A1, u plus bracket v plus w equals bracket u plus v plus w for all u, v, and w in V. This means that addition in V is associative. A2, there exists element 0 in V such that u plus 0 equals 0 plus u equals u for all u in V. This means that there is an additive identity in V. A3, for all u in V, there exists a negative u in V such that u plus negative u equals negative u plus u equals 0. This means that each element in V has an additive inverse. A4, u plus v equals v plus u for all u and v in V. This means that addition is commutative in V. S1, lambda times bracket u plus v equals lambda times u plus lambda times v for all u v in V and lambda in F. S2, bracket lambda plus mu times u equals lambda times u plus mu times u for all u in V and lambda and mu in F. S3, lambda times bracket mu u equals bracket lambda times mu times u for all u in V and lambda and mu in F. S4, 1 times u equals u for all u in V. From now on, unless otherwise stated, V denotes a vector space of a field F, where F equals the real numbers, complex numbers, or F2. Let's see some examples of vector spaces. To begin, Rn, Cn, and F2 to the n are vector spaces over the real numbers, the complex numbers, and F2 respectively. Second, let S be a set. We consider the set of all functions from S to the real numbers, denoted by functions bracket SR. First, let's define addition on these functions. If f1 from S to the reals and f2 from S to the reals are functions, then we define the function f1 plus f2 as follows. Bracket f1 plus f2 of S equals f1 of S plus f2 of S for all S in S. The zero element of these functions is the zero function, that is, the function 0 such that 0 of S equals 0 for all S in S. If f is a function from S to the reals, then negative f is the function such that negative f of S equals negative f of S for all S in S. It is clear that A1 to A4 all hold according to these definitions. Now we define scalar multiplication. For lambda in the reals and f as a function from S to the reals, we define the function lambda times f as follows. Bracket lambda times f of S equals lambda times f of S for all S in S. It is easy to check that S1 to S4 all hold. For example, for S3, let lambda and mu be real numbers, and f be a function from S to the reals. Then, for any S in S, bracket lambda times bracket mu times f of S equals lambda times bracket mu times f of S using the definition. By the definition again, this equals lambda times bracket mu times bracket f of S. Now, lambda, mu, and f of S are all real numbers, so we can change the order of multiplication to bracket lambda times mu times f of S. By definition, this equals bracket lambda times mu times f of S. So indeed, lambda times bracket mu times f equals bracket lambda times mu times f. So S3 holds. Hence, the set of functions from S to the reals is a vector space over the reals. As the third example, consider the set of polynomial functions from the reals to the reals as a subset of the functions from S to the reals. In symbols, we write R bracket x equals the set of all polynomials with real coefficients. Observe that addition of two polynomials gives again a polynomial, and the scalar multiplication of a polynomial again gives a polynomial. We say that R bracket x is closed under addition and scalar multiplication. R bracket x is a vector space over R, and is called a subspace of the functions from S to the reals. The notion of subspaces will be covered in detail in the next video. For the fourth example, we consider a subset of R bracket x consisting of polynomials of degree at most d, where d is a positive integer which is fixed. It is also a vector space over the reals. When d equals 0, the set of polynomials is just the real numbers. When d equals 1, we have bracket ax plus b plus bracket a prime x plus b prime. This equals bracket a plus a prime times x plus bracket b times b prime. Also, lambda times bracket ax plus b equals bracket lambda times a times x plus lambda times b. We can see that there is a one-to-one correspondence between the linear polynomials and R2, namely, ax plus b corresponds to the ordered pair AB. More generally, there is a one-to-one correspondence between polynomials of degree d and R to the d. Now let's look at a proposition. Let D be a vector space over a field F. Then for any v in V and lambda in F, we have 0 times V equals the 0 vector. We start with 0 times V, which equals bracket 0 plus 0 times V. This equals 0 times V plus 0 times V using S2. Now, the 0 vector equals 0 times V plus negative of 0 times V by A3. This equals 0 times V plus 0 times V plus negative 0 times V using the result on the left. By A1, we can swap the order of addition to get 0 times V plus bracket 0 times V plus bracket negative 0 times V. This equals 0 times V plus 0 using A3. Finally, this equals 0 times V using A2. Second, lambda times the 0 vector equals the 0 vector. We start with lambda times the 0 vector, which equals lambda times 0 vector plus the 0 vector using A2. This equals lambda times the 0 vector plus lambda times the 0 vector by S1. Now, the 0 vector equals lambda times the 0 vector plus negative lambda times the 0 vector using A3. Using the result on the left, we have bracket lambda times the 0 vector plus lambda times the 0 vector plus negative lambda times the 0 vector. Again, we can swap the order of addition to give lambda times the 0 vector plus bracket lambda times the 0 vector plus bracket negative lambda times the 0 vector. This equals lambda times the 0 vector plus the 0 vector using A3. Finally, this equals lambda times the 0 vector using A2. Thirdly, lambda times V equals the 0 vector implies that lambda equals 0 or V equals the 0 vector. We only have to show that if lambda is non-zero, then V must be equal to the 0 vector. Now if lambda is non-zero, then the inverse of lambda exists. So V equals 1 times V using S4. which equals bracket lambda inverse times lambda times v. This equals lambda inverse times bracket lambda times v using S3. By assumption, this equals lambda inverse times the zero vector, which is just the zero vector using the second point. Fourthly, negative lambda times v equals lambda times negative v equals negative of lambda times v. We start with bracket negative lambda times v. This equals bracket negative lambda times v plus the zero vector using A2. This equals bracket negative lambda times v plus bracket lambda times v plus negative of lambda times v by A3. Swapping the order of addition, we have bracket negative lambda times v plus lambda times v plus negative of lambda times v. This equals bracket negative lambda plus lambda times v plus negative of lambda times v using S2. Now, this equals 0 times v plus negative of lambda times v. This equals 0 plus negative of lambda times v using the first point. So this is just negative of lambda times v by A2. On the other hand, lambda times negative v equals lambda times negative v plus the zero vector using A2. This equals lambda times negative v plus bracket lambda times v plus negative of lambda times v by A3. Swapping the order of addition, we get bracket lambda times negative v plus lambda times v plus negative of lambda times v. This equals lambda times bracket negative v plus negative of lambda times v using S1. This equals lambda times the zero vector plus negative of lambda times v using A3. This equals 0 plus negative of lambda times v using the second point. This is equal to negative of lambda times v by A2. For the final point, negative 1 times v equals negative v. Indeed, negative 1 times v equals negative of 1 times v using the fourth point. So this is just negative of v by S4.